All right, you just heard from my co-instructor, Jim Jenkins. I'm Bruce Newhall, and welcome you all. As Jim said, I have 40 years' experience in underwater acoustics and sonar signal processing. I came into signal processing starting with work in underwater acoustics, and not knowing much about signal processing. When I got to the Johns Hopkins Applied Physics Lab, I realized there was sort of a niche that wasn't being filled. There were a number of people in the group who knew signal processing, primarily radar signal processing, but didn't know much about underwater acoustics. And there were a number of physicists who knew a lot about acoustic propagation but didn't know much about signal processing. And I decided there was a niche for someone who knows both of those things, and I certainly hope this course will get you started in that direction as well, in both underwater acoustics and signal processing. And I've worked in towed arrays with passive sonar, and I've worked in low frequency active sonar as well. So what are the kinds of things that signal processing does? Well, the first thing is a detection issue. We have some data and we want to know, is there a signal present? And if the signal is present, there's always noise present, so we're actually seeing signal plus noise. Or is the data that we're seeing just the noise alone with no signal present? So that's the detection problem. Once you have made a detection, you might want to estimate things about that detection, like what its frequency or duration is, or you might want to know things about the source that's making the sound, what's its location, what's its velocity, that sort of thing. So how do we best estimate those things? And the signal processing you do for estimation isn't necessarily the same as what you do for detection. The next task that signal processing does, I would call association. Now you have multiple detections. You want to know, are they from the same thing? Are they from the same source associated? For example, one source making multiple frequencies. Or in active sonar, you might have several pings, making a detection on each ping. Are those pings all coming, those returns all coming from the same object? Do they form a track, consistent track? So tracking is a type of association. And finally, classification. You want to know, is the source producing the signal from some certain class of objects? And classification in sonar can be a very broad thing, such as just distinguishing, is it man-made or is it from some biologic source? Or it can be a very specific thing. Is it the port engine on a certain submarine? A very specific kind of classification you might do. We will talk about all of these signal processing tasks in the course. And the other thing I want to say about signal processing in general is that it relies on underlying models. So you have some kind of model for what you think the signal looks like, and you also have a model for what you think the noise is doing. And based on the differences in those two models, you can come up with a best approach to do the signal processing. So it's important that you keep the models in mind, because often you go to a new task, perhaps that hasn't been done before, and you don't just grab any old processing algorithm and apply it to that new task. You want to think about what the models are associated with that algorithm. Are they appropriate for your new task? Or do you need to modify the algorithm based on the differences between what the algorithm assumes for the models and what you think might be a better model for your problem? So I will try to point out as we go through the course, when we talk about different processing algorithms, what the underlying models are, and hopefully that will help you understand when to use those algorithms and when not to use them. Now there is one saving grace in that many of the traditional algorithms are what we might call robust. And that means that even if the signal doesn't quite match the signal that you assumed in your model, or even if the noise doesn't quite match the noise you've assumed in your model, the algorithms still might work pretty well. So we try to get algorithms that are fairly robust to that kind of mismatch, because we know that our models are at best only approximations to the real world, and therefore we try to avoid methods that are highly sensitive to those assumptions. For example, I'll talk briefly about match field processing when we go into beamforming, and that's an approach that's fairly sensitive to the details of the propagation environment and is very hard to apply in practice because of that sensitivity, and is generally not favored in practical systems. Okay, so that is my brief introduction to signal processing, and now I'll turn it back to Jim.
First, I'm going to use your computer, if you can, either from the thumb drive or
Yes.
pick up my material.